Hello, physics students. Welcome back. This is the unit we're going to do is the study of motion. Okay, motion, movement of any type, and we're going to study it in one dimension, and then we'll add another layer by studying motion in two dimensions. And then your next question could be, how about three dimensions? We live in a three-dimensional world. Yes, the same rules that we will apply in one and two dimensions apply to three. We won't really get into that too much. It's more of the same, with a little bit more trig stuff involved than what we do, but it's really not bad. But it's, we study one and two. We'll go up to two dimensions and we'll study that. And it's one of this is one of the units where you actually get to see it. And I mean, all of physics, most of physics is you get to actually see stuff and then describe it and then quantify it, which means put numbers to it and then use that to predict future outcomes, which is great, which is what science is about. So I've put up the equation sheet, which is now downloaded into, so this is the equation sheet that you should download, and if you can, print off, and you can write on this, make notes on it, and this will be a reference sheet for you for the entire year. And your own little notes are good too, so you can personalize it to describe things, and I would highly encourage that. So laws of motion, we're going to be doing, we're doing this next, and then energy and power next. So, but right up here in this top half, this will be a great little guide or reference for you for the problems that we solve. Don't let it intimidate you. There's just variables, and we're going to talk about the variables here in a little bit. But so that is a velocity, final velocity. That variable is an initial velocity. That variable is acceleration, and delta x, where delta stands for change, it's a Greek letter, change in x, and x stands for position, so this is displacement. And I'll go over all these again. That's displacement. And then we're missing one. The other one here is time. So there are 5 total variables in these 3 equations that you're going to use a lot. And those 5 variables are time, t, the final, velocity final, initial velocity, acceleration, and displacement, which is change in position. Okay, now this one we'll talk briefly down here. This is distance. And you're like, what is that? How is that different than displacement? We'll get there. So displacement is change in position. And distance is the distance traveled, and this is rate, which actually you can please write on here, this is speed for us. And that is obviously time. So this is for constant or average speeds, where r is the speed. So please make sure you note that r is the speed. Now these two are just describing what velocity, average velocity, and average acceleration are, and we'll get to those more here in a little bit. And we have help, unit help. These are basically the SI units for these individual things. It doesn't mean it will be exactly what the problem's looking for. So displacement, you might need it in feet in a certain problem. But our standard SI unit is meters. Distance is meters. Time is seconds. Velocity is in meters per second. Speed is in meters per second. Acceleration in meters per second squared. And we'll get to all that. But that's the equation sheet, and it's uploaded into Kappa. And it'll be in the Google Classroom upload. It'll be downloadable in the Google Classroom too this week. So make sure you get that definitely on your computer. Okay, so now we're going to go to, there we go. And we're going to talk a little bit about one-dimensional motions and frames of reference. So we're going to start on 1D motion. What does that mean, one dimension? Well, it means, suppose we have, oh wow, that was bad, but let's forget that. Suppose we have a path here. You're walking in a straight line. You have a person here. And they're walking this way. Or maybe this way too, right? That's one dimension for us. Also, suppose we have a rocket go straight up, or a ball is thrown straight up, or something is dropped, a penny is dropped. Okay? This is motion in one direction too. So we will study motion in one dimension in the up-down direction, and the left-right direction. So that'll be our initial study in this unit, is motion in one dimension. Okay. Now, when we put signs on things for motion, positive will mean to the right for direction on an answer. Negative will mean to the left for direction. All right. Okay, what about in vertical? So this was horizontal. This was horizontal right here. And so in the vertical, plus is up, negative is down for direction. For direction here in the vertical. Okay? And this was horizontal direction. Okay? So that's how we're going to notate that. Positive right, negative left, positive up, negative down. Okay? So let's go to a new sheet here, and we're going to talk about frames of reference. So, frame of reference is just your starting and ending of your viewpoint here. So we could have, say, a turtle, right? There's my turtle, and they walk here to here, and they walk here to here. Okay, and so this is, say, 1 meter, and this is 2 meters, and then the turtle ends here. Then, after that, the turtle turns around. Turns around, there's his tail, there's his eyes. Okay, and then he walks, so he walked this way, and now he's walking back, and he walks back to here, and he ends up here. All right. So, what could happen is we have a frame of reference. What is our frame of, when's our start and end? You get to make that. What is your world? So in this case right here, if you say that I'm starting his first trip, then my frame of reference is here. Start, end. Okay, you're not even worried about this part down here. This is your world, this is your start, this is your end. You could say my starting position is 0, my ending position is 2. So, what is my displacement? I can go calculate this stuff, and we'll do that. But what if our start was here? Suppose this was our start and this was our end. That's a separate frame of reference. And in some problems, you may want to make it two or three frames of references, right? So where is your starting and where is your ending? That is your world. That is your frame of reference. You could have just as easily said, change it to orange here. This could have been your start, and this could have been your end right here. So the turtle went here, and then he went back. And that's your start, and that's your end, and that's your frame of reference. So your frame of reference is just your viewpoint, okay? And we'll get more into what this means as we solve problems, all right? So that's a little bit on frame of reference, immensely important for us. Whoops. All right, let's go to a note. Pause for a second. Okay, so now I'm going to define variables real quick, and we'll get more into variables individually too, but I want to define them, and I just mentioned them on the equation sheet part. Okay, T will stand for time for us. In typical units, we'll put like a typical SI units over here. Okay, so System International Units would be the second. We'll do that as there, second. Other units, though, you might see are minutes or hours, so we have to learn how to deal with those as well. Okay, let's do displacement. So delta x is change in position, which is also called displacement. And that will be in meters, is our SI unit. Okay, velocity is change in position over change in time. Okay, but I'll usually just call that, I'll just call time, and not, sometimes I drop off the delta. It's really change in time, but sometimes I'll just call it time. So change in position over change in time, and so that's also called displacement over time. And that for us, our units are meters per second, which is m over v. Those are standard. It could be other things like feet per hour, but that's our standard. Miles per hour, that'll be our standard. That's an S. So for seconds. Acceleration is change in velocity over change in time. So hold on, change in velocity over change in time. And what does that look like? That's delta V, or change in V, over change in t, which is final velocity minus initial velocity, that's change, over time. That's our simplified kind of view of it there. So that's acceleration. So if you were, acceleration is how fast is your velocity changing. So I think of it this way: if you're in your car and you push the gas pedal really hard, you could be going, suppose you're going 60 miles per hour and you push your gas pedal really hard, and that's a very sharp change in velocity. If you push it really hard, you're changing really quickly, right? You're going 60, but that didn't matter. Your acceleration can be big even if you're going slow. Suppose you're going from stop and you slam the gas pedal. You are going to have a large acceleration, right? And you can feel it as it pushing back. That's forces, and we'll talk more about that later too. But this is a sharp acceleration can happen even if you're not moving at all, because acceleration is only change in velocity over time, not how fast you're actually going. Okay, so that's the acceleration. Acceleration is how fast are you changing your velocity. So that's why it's change in velocity over time. Another unit for this, by the way, is meters over seconds over seconds. And so that's equal to meters over seconds squared as a typical acceleration unit. Okay, because it's change in velocity over change in time, right? So that's what that means. So if you slam on your brakes, that's a large negative acceleration because that's the direction of the acceleration. Okay, so now some of these quantities are vector quantities, and some of these quantities are scalar quantities. So we're going to talk about that here in a minute. These are the four variables, but Mr. Nushat, you said there were 5 on that equation. Well, remember, we can have an initial velocity and a final velocity in that. So that is what that's where the 5 variables come from. So on that equation sheet, you have 5 variables: initial velocity, final velocity, a, t, and delta x. Every time you solve a problem, one of our Kappa problems, it's a good idea to have these written down. And if you can find 3 out of the 5, any 3 out of the 5, you can solve using those kinematic equations, right? Those kinematic equations, which are up here. No, they're not up here. They're right here. Those kinematic equations are right here. These are the kinematic equations. If you have 3 out of the 5, you can solve, because every one of these only has 4 variables in it. They're different 4 variables each time, and you might have to find the correct one. But if you have 3 out of the 5, you know you can find an equation and solve for the other one, and then use another equation to solve for the last one. So a lot of these first problems, Kappa problems in this, or a lot of them in general, are finding these 3 of these 5, and then going to town with your algebra. Okay, so I'm going to stop the video here. That's long enough, but we'll have part 2 coming up.